Right, good morning. As most of you know, work on lasers, and one of the things I'm particularly interested in is ModeLock lasers. So let's go. Oops. How do I move? Right. I'm going to show a slide on some of the motivation. Then I'd like to give a brief introduction to ModeLocking lasers because I don't think most people know how they work. Then I'm going to describe the work that we've done on ModeLock lasers, looking at 40 gigahertz ModeLock lasers and the effects that we've been able to, looking at the structure, the geometry of the laser and the epilayer structure, changing that, and then a quick summary. And I'm between you and coffee, so I'll be as quick as I can. Right, ModeLock lasers are basically used in applications where you're looking for short pulses, particularly at high frequencies. With the semiconductor lasers. Semiconductor lasers ModeLock most easily at 10s to about 100 gigahertz. And that's related to the length of the cavity. That's the pulse round trip time. Bigger lasers give out more power and operate at much lower frequencies, down to the megahertz range. But they could be useful for the next generation of TDM at greater than 100 gigabits, all optical recovery, clock acquisition, ultra-fast signal processing, high-speed sampling, where you put in electro-optic sampling, where you put in an optical pulse and look at the electrical response, microwave and millimeter measurements, fiber radio, transmit high-frequency signal using optical fiber and ModeLock pulses to small transmitters that are local transmitters, low power, analog to digital conversion, high-speed logic. Right, how do we make a laser ModeLock? Well, any laser that there is has several modes, and the intensity, the output intensity, is just a sum of the square of the electric field of these modes. These modes add up. Now we have the here the amplitude of the electric field, and this is the mode frequency, and then there's this term here which is the phase. And that phase normally is random between modes. And if we look at it, you can see here, this is some modes, and this is time along the bottom axis, and you can see that there's a random relationship which changes with time between the different modes. And the output you get is CW with some noise on top of it, as modes. As the phase relationship between the modes change, the way that this adds up changes slightly, so you get some noise on top of the CW. Now, if you can get into this situation where at one point in time all the modes are in phase, these will all add up and give you a high intensity pulse. What happens when they're out of phase, if it's properly locked, they add up to zero. All the modes will add up to zero, and all the intensity of light is in this ultra short pulse. How we do that? We use a saturable absorber. We put a saturable absorber in the cavity, and this is called passive mode locking. There are other forms, but I'm not going into them. Basically, with a saturable absorber, the absorption decreases as the light intensity increases. You get a graph something like this. At low intensity, you have high absorption, which as you increase the intensity, it decreases. Quantum wells will work very well in doing this, because if you've got light at the band gap energy, once you've filled up the states and the bottom of the wells, that well will no longer absorb. So a short length of quantum well acts well as a saturable absorber. type of lasers the material that I'm going to talk about is quantum well material. And first of all, I'm going to talk about this structure, which is a traditional structure. The lasers are operating at 1.55 microns, so we're using slightly strained aluminium, gallium, indium arsenide wells, which are grown on an indium phosphide substrate. And at the bottom here we have the indium phosphide substrate and a cladding layer which is N-type, is doped N-type. On the top we grow P indium phosphide, and on top of that there will be a contact layer which is indium gallium arsenide, which is highly P-doped. In the middle, in between, we have the waveguide, which is intrinsic and contains 5 6 nanometer quantum wells, which are the gain medium. The quantum wells are what give you the gain. That's where the carriers collect, and that's where the stimulated emission occurs to give the light output. We have both the electrical confinement and the optical confinement. With this smaller band gap, we have a higher refractive index, so this forms the waveguide 2. Now, this is a traditional structure, which is basically what's used in the lasers used in optical communications for the transatlantic cables, any other situation. What we wanted to do was get higher output power. So we took some lessons from the high power community, the high power laser community, and what they've done is, interestingly, reduced the number of wells, but also they introduced this far field reduction layer, which is a weak waveguide on the N side of the substrate, of the active layer, I mean, so down towards the substrate. Now, what this does is affects the optical field. If we look in the optical field in this structure, you can see that the maximum is in the middle of the quantum well layer. Here, it's being pulled over towards the N-side layer, and it does two things. It's reducing the overlap with the wells, but it also reduces the overlap with this P material, and that reduces the free carrier absorption. The free carrier absorption coefficient is much higher in P-type doping than with N-type doping. The photon hole cross-section, interaction cross-section is much higher. So what they're doing is they're reducing the losses in the cavity in order to get more light out. So we wanted more power out of the ModeLock lasers, so we decided to try and use this structure. This is basically a ModeLock laser. This is the bit of semiconductor, and these are gold contacts, and this long contact is the gain section. This short contact here is the saturable absorber. That's about 2% of the cavity length. We have a 10 micron isolation gap where we etch the contact layer between the two contacts, between the gain section and the absorber section, so we don't have current leaking into the saturable absorber. And the cavity length here is just over 1 millimeter, and this gives us a mode locking frequency of about 40 gigahertz. The saturable absorber itself is about 25 microns in this device. And as I said, the output wavelength is 1.55 microns. This is just a picture of the cleaved facet where you can see we etch ridges, and the active region is here just below the ridge. It's single lateral mode, so we have a nice round oval mode here, and this is the metal cladding, and you can see here the silica passivation layer, and there's none on the top where we inject current through the top of the ridge. Light current characteristics, this is the output power against the gain current, the current injected into the gain section. If we forward bias the gain section and the saturable absorber, we just get Fabry-Perot laser. And this is, these different curves are increasing amount of voltage on the saturable absorber. They will mode lock with 0 volts, but to sweep the carriers out faster and improve the recovery time of the saturable absorber, you apply a voltage. And as you can see, as you increase the voltage, the threshold current increases slightly because you're increasing the losses. It absorbs more light before it saturates, and also the slope efficiency decreases again because of the higher losses. This is the RF spectrum. Basically, we couple the light onto a fast photodiode and measure the RF signal from that photodiode, and you can see it's operating just about 40 gigahertz. There's no pulses obvious down here, which would be a sign that it's not mode locking properly. Now here we look at what we call the autocorrelation trace. Here we split the pulse in two and recombine the two halves in a nonlinear crystal which generates second harmonic, the second harmonic of the light. That intensity is proportional to the square of the intensity in the instantaneous intensity. So if you've got the pulses separated, you have a much smaller signal than when they're overlapped. And this is just a function of time, and this is just showing the pulses, a train of pulses. Here we have a single pulse, and the pulse length for this is about 1 picosecond. This is not a correlation trace of single pulse. And that's the optical spectrum, which is a nice clean spectrum showing plenty of modes. Now when we compare the performance of the new structure, the 3 quantum well structure, with the 5 quantum well structure, just looking at the CW output power as a function of injection current, you can see we get powers that are at least twice as much coming out, twice the power coming out before it starts to roll over. This rollover is due to heating, which is caused by the light being reabsorbed in the cavity, and non-radiative recombination, which should be small, but it's mainly the reabsorption of light. And you can see that reducing the overlap with the P cladding layer has helped that immensely. This is a comparison of ModeLocking Map. What we have on both graphs is a map of the gain current against a saturable absorber bias, so with the gain current and saturable absorber bias. The red area is where we see good mode locking, and you can see that with the 3 quantum well device, this red area is much higher, is much larger. The blue bit down here is where it's not mode locking. One of the things to note is that if you drive the current high enough, the device stops mode locking. This is because the saturable absorber is not absorbing enough of the light that's oscillating within the cavity to cause mode locking. If we look at the peak pulse power, we can see this is the peak pulse power against gain current. This is misleading because the two, this is a much finer scale than this one. You can see this only goes up to 50 milliwatts, this one goes up to 120 milliwatts. So the pulse output power we're getting is about 3 times that with the 3 quantum wells compared with the 5 quantum well. If we look close up at the peak that we find in the RF frequency, for the 5 quantum well device, we find that the width is 36 kilohertz. For the 3 quantum well device, that's reduced to 25 kilohertz. This is a measure of the pulse stability. The resolution bandwidth of the equipment was 10 kilohertz. The narrower that is, the more stable the mode locking frequency is. And we also see that when we measured the timing, calculated the timing jitter between pulses, it's 4.7 picoseconds for the 5 quantum well structure and 1.2 picoseconds for the 3 quantum well structure. Why is this happening? Well, this here is the material gain as a function of the sheet carrier density. That's basically, the sheet carrier density is basically how much current you're injecting. So if you look here, the one that I particularly want to look at is this indium gallium arsenide quantum well. You can see that as you increase the current, the gain increases rapidly to begin with, and then it rolls over to less rapid. Most 5 quantum well structures are operating here. Our structure's operating up here, where the gain change for the change in carrier density is much smaller. Now the gain is related to the refractive index through the Kramers-Kronig relationship. So if you have less change in gain, you have less change in refractive index. And we have a dynamic equilibrium in that the carrier density is changing slightly. Even though we're injecting a constant current through the cavity, the carrier density is changing slightly. So when the pulse is propagating around in the cavity, the carrier density and the refractive index is changing as it goes through. But if we operate up here, the change in refractive index is smaller. The change in refractive index causes a change in speed. So that means that the change in speed from pulse to pulse is smaller if the change in refractive index from pulse to pulse is smaller, and that leads to the more stable mode locking and the lower timing jitter. Another thing that we looked at was to introduce a passive section into the cavity, and we did this by quantum well intermixing. Basically, you take these nice quantum wells that the grower spent all the time perfecting, and then pattern the top so that you have a cap that will cause point defects to diffuse through them and get the wells to intermix with the barriers. And that means that why we do that is to increase the band gap. So the band gap here is larger than the band gap here, so the light generated here is not absorbed here, even although we're not injecting current. This again is just over 1 millimeter long, so we have comparable mode locking frequency. If we look at the light current characteristic, this is a Fabry-Perot laser without the passive cavity, and here we have the mode locking laser with the passive cavity. We have a distinct increase in threshold current due to increase in losses because of the satchel absorber, and there are some losses in that passive section, but they are relatively small. The power output is also a bit lower. If we look at the ModeLocking Map again, this, as we showed before, the gain current against the saturable absorber bias, you can see in this case we have a much larger area where it's mode locking. The other thing that we found was the mode locking pulses, the pulse width is very even throughout this area. Compared to, this is for a cavity without the passive section, you can see that as you increase the current, the pulse width goes up, the pulse length goes up. Here it remains very flat. And this is due to the fact that we have reduced what's called the self-phase modulation. As the pulse goes through the cavity, front of the pulse sees a slightly different refractive index from the back because it's caused stimulated emission and reduced the number of carriers as it goes through, so the back of the pulse has a slightly different refractive index. In the passive section, this doesn't happen because we're not taking out any carriers. So we've reduced the self-phase modulation, and that self-phase modulation causes the change in refractive index, changes the speed of the light as the pulse goes through the cavity. Within the pulse, it's changing the speed of the light within the pulse and spreads it out. By removing some of that self-phase modulation, we've managed to narrow the pulses, and it's meant that increasing the current has had a smaller effect on spreading out the current pulse. When we actually measured the current pulse, we find that the pulse length is about 490 femtoseconds. So by changing the design of the epi layer, we've managed to improve the timing jitter from these devices, and by introducing a passive section in the cavity, we can reduce the pulse length. Thank you.
Time for a few questions.
What's the highest power output that you can get from a chip-scale mobile player?
Right, the highest power we've seen out is about 60 milliwatts, I believe. No, maybe 30 milliwatts. The structure that I showed you to begin with, you only get a few milliwatts out. We managed to get that up to about 30 or 40 milliwatts. We have integrated amplifiers and managed to get out much higher powers, coming up to a watt, and several watts peak power.
And what kind of line width do you get?
Oh, these are broad because we need several modes. You know, the more modes you can lock together, the narrower the pulse.
The individual lines.
The individual, we've not looked at that. We've not been interested in that.
Let's thank all our speakers again. We have about 15 minutes for a break, and then please return for another one of our